Hey everybody, this is Franco, and today we're going to talk about FANUC G68.2 5-axis tilt at work planes. So why do we care about that? Well, if you only work in 3-axis, that's all you ever do is work in 3-axis, then you may not care about FANUC G68.2 tilt at work plane. But if you're working on a machine with a 4th or 5th axis, like the machine I have on the screen, then tilt at work plane is a really big deal. So this machine has a 4th and 5th axis. So what we see here is this rotary unit, it can tilt in an axis that's through the y-axis. That would be the b-axis. And it can also rotate in an axis through the z, which would be the c-axis. So this machine has a b and a c-axis. And that's useful for making parts with lots of different faces, right? So if you look at this little part I have on here, you can sort of tell it's got multifaceted faces that are not all at 90-degree angles to one another. So this isn't really a 3-axis part. It's not really a 5-axis part either. What it is a 3+2 part. So back in the old days, the only way to really attack a part like this, assuming that you had rotary axes, before tilt at work plane existed, there were 2 ways to do this that I'm aware of. One is you could make a different work offset for all these different faces, all these different positions of the B and the C axis. You would create a different work offset, G54, G55, 56, 57, 58. If you have extended work offsets, you could use those. And what you would have to do is manually kind of like find these positions for all these different faces of the part. So it's really tedious, takes a long time, it's not very efficient. The other way of doing it was to program all your rotary moves from the center of rotation. So what does that mean? Let's see here. So what you would have done is in your CAM model, you would have found the theoretical point where the B-axis and the C-axis intersect. It would be on this machine, it would be somewhere like in here. And you would call that basically your work coordinate system. You would make that your XYZ0 in your part setup. And then all of your motion, all of your rotary moves, everything would be relative to that point. And it sounds good, right? It sounds like it would get the job done. But the problem is it doesn't do a very good job of taking into account these like very small differences in the machines in the setup. So no machine is perfect. If you've worked on any of these 5-axis machines, you know none of these rotary units are really truly perfect. They all have some error in them. If you have multiple machines that the jobs move between, they're all going to be slightly different. So what happens is you wind up hard coding all this stuff into the program, and then every time you have to make an adjustment, you wind up going back to the program and changing it. It's not the best. It's really not the way to do it. So that's why a function called tilt at work plane, FANUC G68.2, was created. And what it does is it uses the control to keep track of all these things. So inside of the CNC control, there's a parameter that defines the center of rotation. It's a parameter that defines where the B-axis and the C-axis, in this case, would intersect. And then the control does all this math for you automatically, and makes it much easier to set the jobs up and make adjustments and bring the jobs from one machine to another. So like for instance with tilt at work plane, you can call this point up here on top of the part, you can call that XYZ0. In fact, you could call any point in space XYZ0. It does not have to be the center of rotation. It can be any point anywhere, can become your origin for your program. So that's what, in a nutshell, that's what tilt at work plane is. If we go back over here, I'll put links in the YouTube, or links in the description of this YouTube video. There's a really good article on LinkedIn that describes how this stuff works. And I think if you just search it, do a Google search for FANUC G68.2, this is going to be one of the first things that pop up. So I'm not going to try to reiterate everything that's in this article. This person lays a lot of this out for you, and they give you some examples, and then they talk about the different types of G68.2 that has, what do we have, 5 different modes. We'll get into that in a second. So what this is this is a way to define the tilde plane, to define the new plane. So if we jump into Fusion 360, we'll use this part as an example. This part, you can see this is its setup. This is how the part sits in the vise in the machine. And right there is the XYZ origin for the part setup. But when I start to get into these features that are not, what would we say, normal to the part sitting in the vise, all these complex facets, you can see that the axes have to change, right? It has to tilt. And the way you do that in Fusion 360 is really simple. You literally just click on a face or click on a feature, and Fusion 360 knows that it has to tilt to get to it. And that's what creates all these changes in the rotary axes. So the normal setup was up here, but when we attack these complex faces, we can see that it has to tilt. So there's a way of specifying this. That's what G68.2 does. It specifies these changes. And that's what we're going to get into. So if you come over here, well, you know what? There's actually a better way of doing it. Let's do it this way. So let's take this right here, this toolpath. I'll simulate it so you can see what we're doing. All right. Slow it down a little bit. So this toolpath, it's going to come down and cut that flat. But you can see our rotary axes had to move to present the part to the spindle in the correct orientation. So let's just take that toolpath and let's post it out. All right. So what we have here, I'm not going to go over all the different pieces of this program, but I'm going to focus on the part here that really matters to me right now. There's a move here that pre-positions the B and the C axis. So it pre-positions those rotary axes. Then it fires off this G68.2 command. And this is what's defining that tilted plane. And then it does G53.1, which is a really powerful command. Is what it does is, now that tilted plane exists, G53.1 causes the rotary axes to move in such a way that the new coordinate system, the z-axis of the new tilde coordinate system, is in line with the z-axis of the machine. Now, what happens is, Fusion 360, what it does is it pre-positions those rotary axes. So when this line is fired off, it's actually in position. So we'll talk about that in a second too. But it's going to take the shortest distance to where it needs to go. If it happens to be sitting in a position that resolves the problem, then there is no physical motion because we've already pre-positioned the rotary axes to a point where all this math can work out. But what always has been a little bit of a challenge for me is when I read this line, I've always struggled to understand how this line of code translates into this. It's always been a mystery to me. I could never really figure it out, but I finally figured it out with some help from a few other people who are smarter than me, so I'm going to make this video to try to explain it to everybody else. All right, so back to the LinkedIn article. So essentially what is a really important thing to understand is there are 5 different modes for FANUC G68.2. So there's 5 different ways for the control to define the new tilt-at-work plane. There's what are called Euler angles. It looks like Euler. When I read this, to me it looks like it should be pronounced Euler, but it's actually the proper pronunciation is Euler angles. There's roll, pitch, yaw, 3 points, 2 vectors, projection angles. I've only ever seen this first type used, Euler angles. But according to this article, roll, pitch, yaw is really popular. And in the article, this gentleman explains all his examples using roll, pitch, yaw, which for me didn't really help me very much because everything I've had to work around uses Euler angles. So what are Euler angles? If you follow the links, it'll take you to some really good LinkedIn article or Wikipedia articles that'll explain what Euler angles are and how they work. I would encourage you to look at them. I'm going to try to explain in a second here too. And this gentleman, Leonhard, I think he's Swiss, Leonhard Euler. 300 years ago, this guy was like a genius, and he came up with all this like really important mathematical stuff. But I guess one of the things that he came up with is a convention for defining the position of bodies in 3D space, and his convention are called Euler angles, and that's what the default mode. If you don't specify what mode you're in, if you just fire off a G68.2, the default mode is to be using Euler angles. So that's important to know. So when we go back to our code, we can see there's no P specified on this line, so it's defaulting to Euler angles. That's really important to understand and decipher these numbers. So the way this works, the X, Y, and Z, basically what that's doing is it's picking a point in space that we're going to pivot about. The I, J, and K specify the Euler angles. And what's interesting is the way Euler angles work is it's not X, Y, Z or A, B, C. It's Z, X, Z. So this was the thing that I never understood until just recently. So I'm going to demonstrate this in a second. So the X, Y, and Z is like picking a point in space wherever you're going to rotate around. And then the I, J, and K are the I, J, and K are the Z, X, Z rotations. So let's go look at an example of that. So we'll use this toolpath, face right compound. And you can visualize in your mind, you can see the tilt, right? Obviously the Z-axis has to be normal to that face, and then Y and X have to move accordingly. And remember, just as a point of reference, if I click on the setup, you can see that this is where our part sits in space as far as the CNC program goes. This is how the part is set up. We have to do a tilt-at-work plane to get to this face. So we have to go from here to there to cut this face. And that is what this line of code is doing. So let's look at an example here. So what I have this nifty little thing that I made up. We'll say that this is the base coordinate system. This is like the coordinate system that the part is sitting in when it's at B0, C0. X, Y, and Z. Colors match this up here. X is red, Y is green, Z is blue. And then what I have is a new coordinate system. This is going to be our tilde plane. This is going to be our tilde coordinate system. And if you notice, the tilde coordinate system is just a little bit bigger than the base coordinate system. And let's see here, my screen is being obstructed by my window is being obstructed by my screen capturing software, so let me move some things around here quick just so I can make this work. Okay, we'll do the best we can. What I've done here is I've created some parameters that I'm going to use to walk through this. So x, y, z, I, j, k, these relate to the x, y, z, I, j, k in the CNC code. And now we'll notice the x, y, z, they're all 0. So what that's saying is that the pivot point of the new tilde coordinate system is the exact same point of the WCS of our part definition. Now, if for some reason we didn't want it to be that way, right, you could shift it. I've never seen this done on a milling machine. Every milling machine I've ever seen programmed, the X, Y, and Z are always 0. But the function has the ability to shift the point around which you're going to tilt. Now we're not going to do that because that's not what's in our code. But I just want to illustrate that. That's what the X, Y, Z is. X, Y, Z, those are values that will move the pivot point to some point in space. And then that's the point that we would pivot around. I've never seen this used on a milling machine. Milling machine, this is always 0. But I have seen it on a lathe, on a Swiss lathe. The way some parts have been programmed, they would shift before they do the tilt. But I've never seen it on a milling machine. It's always X, Y, Z, 0. Now the I, J, and K, these are our Euler angles. So the first value, I, remember, it's really a Z, X, Z move. So this first value, it's 168, right? I'm going to copy that. This is a shift, this is a rotation around Z. So I'm going to take that and put it right here. So that was a rotation around the z-axis. Now, initially, the z-axis of the tilde plane and the z-axis of the base coordinate system are identical. But what it is it's a rotation around the z-axis of our tilde coordinate system. Now, the next rotation is an x rotation. Now that, what it is a rotation around the x-axis of the tilde coordinate system. So just to clarify this, let me hide the tilde. This is our base coordinate system, right? It matches this little thing up in the corner here of fusion. Now I'm turning on our tilde coordinate system, and you can see it's just a little bit larger than the base. This rotation is about the x-axis of the tilde coordinate system. So now I have the tilde system turned on. This rotation is around the x-axis of the tilde system. So I'm going to put that value in there. Now it tilde it. And now this final value, turn on, there's the base, just as a reference. I'm going to turn it off because I think this is easier to see without it on right at the moment. The final rotation right here is around the z of the tilde plane. There's our rotated coordinate system. And I'll just hide the parameters. I'll turn the base back on. So now you can see what we have. If you can imagine this, there's our base coordinate system. And there's our tilde coordinate system. You can sort of see what we have there. Remember, the base is the small one, and the tilde, right? So you can see how it's tilting to match up with our part. So let's go look at our part. And I think it was face left compound, right? So if you can visualize this, this is the face we were machining. Maybe get it in your mind, just how it's sitting there in space. We had to get the tool normal to this face. Whoops, face right compound. And I can tell you that that is what we have here. So let's try to pick something that's maybe a little easier to visualize. Let's pick a different toolpath. Let's go with this bore right here. So we can see that basically all we did to get to this bore is it appears that we just tilted around x-axis. So that's where we start, and that's where we're going to go. And let's just simulate that just to give you an idea. So this is what we're doing. Going in there and machining that bore. Machine simulation stuff is pretty cool in Fusion. I'm really glad they're implementing that. So let's post-process that operation. Okay, same thing, pre-position, and then we fire off the Euler angle. So once again, it's x, y, z, 0. So the tilde plane shares the same pivot point as the original WCS. But now we have the rotations, a z rotation, an x rotation, and then another z rotation. 180, 45, 180. So you can picture in your mind how we're tilted. Let's go back over here. Let's just change this. So I remember it's 180, 45, 180. And that, you can see, this is the tilde, right? There's the base, there's the tilde. You can see how it matches up perfectly with our part. Right? So I could go through more examples, but hopefully seeing this is helping it become more clear. The real key for me was that this is a ZXZ. That's what the Euler angles are. It's a rotation about Z, a rotation about X, and then another rotation around Z. And it's based on the tilted plane. So we'll start over again here, just make these all 0. Right, in the beginning, the tilted plane and the base coordinate system, they're on top of each other essentially because we didn't shift in X, Y, Z. First we tilt around Z, 180, right? And then this is the x-axis of our new tilted plane. We come over there, we tilt 45. And now we're going to tilt around the Z of our tilted plane, 180. And that positioned our tilted plane exactly as it's shown here on our part. And those numbers were taken directly from the program. So now we can correlate what's in the code to what the machine is physically doing. I could never do that before, but now I understand it. I'm really excited about it. The last thing, this G63.1, this is really like the real powerful piece of this. What this does is it moves the rotary axes in a way it puts the z-axis of the tilde plane, makes it coincident, puts it in line with the z-axis of your spindle. Now, the x and the y, obviously, they just kind of go where they need to go to make that work. So that's why when you're using these commands, an x move or a y move, if you make some kind of adjustment, for instance, it isn't necessarily going to be in alignment with the physical x and y of your machine tool. Something has to give, right? So they just kind of rotate wherever they need to rotate. But the main thing is your z-axes have to be in line, right? The z-axis of your tilde plane has to match the z-axis of your machine. Now, in many cases, there can be two solutions that work. On this machine, in this position, there isn't. There's only one solution that works. But depending on how much you're tilting and how much travel your rotary axes have, there could potentially be two rotary axis positions that will achieve the same result. And that's why when you're post-processing, and hopefully I'm not going to make a liar out of myself. Let's see. Many post-processors have a parameter in here to show a preferred tilt. And let's see, I'm either missing it or it's defined someplace else. I think in this post processor it's defined someplace else. I think we actually did a customization on this post, so we're defining the preferred tilt using a manual pass through. But for many post processors, what you'll see is a parameter somewhere where it asks for the preferred tilt angle. It might be you'd want to prefer that B always tilt positive or that B always tilt negative, and the reason being, depending on how your machine is configured, you may find that if you tilt negative, you can see the part better while it's being machined than if you tilt positive. So that's just something to keep in mind. All right, well, hopefully that helps explain a little bit, clears up how G68.2 works. Thanks for watching, and have a great day.